Hello. I would like to start by thanking the opportunity to present this topic in this Eurachem workshop. In my talk, I will describe the principles of top-down uncertainty evaluations based on in-house method validation, and I will try to discuss how the most challenging goals of this type of evaluation can be managed. Top-down uncertainty evaluation and specifically the ones based on in-house method validation are very popular due to the simplicity of the calculations and due to the fact that that simplification does not overestimate the measurement uncertainty too much. So this process typically will not affect the production of fit for purpose measurement uncertainty or adequately low measurement uncertainty. However, some challenges have to be faced if we want to make this evaluation efficient and if you want to produce reliable uncertainty evaluations. Some examples is how to handle the variation of the uncertainty in a wide concentration interval, how to use all reference materials available for trueness or bias assessment, how to handle bias, and in some fields where you have regulated method validation design, how can you use that design to evaluate your measurement uncertainty? Because typically this design was not defined having in mind the need for this uncertainty evaluation. So we know that this top-down approach based on in-house validation data includes or involves the quantification of the uncertainty from precision, typically precision under intermediate precision conditions, so between days precision, I would say. And then we have the trueness uncertainty or bias uncertainty. And occasionally, depending on how your measurement is defined, you can have other uncertainty components like sampling uncertainty or others. We know that measurement precision varies with the concentration, and this is important for methods applicable to wide concentration intervals. And trueness uncertainty should not usually is not changing so much with the concentration. And but instead depends on the reference materials that you have available to assess that trueness. To make sure that trueness does not vary very much with the concentration, we have, for instrumental methods of analysis, we have to make sure that the regression model used in calibration is fit for the data. If you use a linear model, you have to check linearity of the response of your instrument. And now let's try to discuss the first challenge, how to model precision variation with concentration. So we know from how limit of quantification and limit of detection are defined that the coefficient of variance at these two levels is 10% and 33% respectively. And ideally, these limits should be estimated under intermediate precision conditions to make these limits stable in different days. And we also know that typically the intermediate precision standard deviation is constant in a narrow concentration interval and typically increases with increase of the concentration interval. And if we look to the relative standard deviation of the intermediate precision, we know that it decreases in an abrupt way from low to higher concentrations. At LOD it is 33%, LOQ 10%, to LOQ 5%, and after that it becomes rather stable, rather constant above that concentration. So if we have that information into consideration, we can take all available estimates of the intermediate precision standard deviation in the narrow interval LOD to LOQ, LOQ to LOQ. You can change this by LOD if you want. So if you have samples being analyzed in different days in this interval, you can pull them and get estimate of the intermediate precision standard deviation in this interval that we call interval 1, and in that case we just need to pull all the relative standard deviation of the intermediate precision that you have from different samples analysis. We can pull them and build a worst case model of how this relative standard deviation varies in above 2LOQ. So you just need to pull all the available information. If you want to improve your model, you can even divide this interval in two shorter, smaller intervals. For instance, between 2LOQ and 10LOQ and above 10LOQ, and you have two-step models of two pooled relative standard deviations to model how precision varies with your concentration level. So, and what about trueness? One of the challenges of trueness assessment is how to use all available reference materials like certified reference materials, proficiency test samples, and spiked samples without native analyte. How can we take all of them and to assess the so-called systematic effects? Typically, we assess recoveries from the analysis of different materials. A recovery is the mean of observed value divided by the reference value. Okay, so if you have n certified reference materials, you have n mean recoveries, and you can calculate the overall mean as the mean of all recoveries. And this formula is fine if typically we have same number of reference materials. If you do the replicated analysis of the reference materials using the same number of replicates. If you have many more from one than from the other one, you can calculate a weighted mean if you want. That depends on degrees of freedoms of all estimated mean recoveries. But in most of the cases, you can apply this formula. And if you use this formula, you just need to know the standard uncertainty associated with the overall mean recovery, or the trueness uncertainty, or trueness standard uncertainty. That will be the ratio between the square root of the sum of the square of the mean recovery for each reference materials times the variance of the recovery observed from the analysis of each material divided by the square of mean recovery observed for that material, number of recovery tests, and then for each material we should also have the square of the relative standard uncertainty of the reference value. So if you have this term for each reference materials, and if you divide all the square root by n, you get the standard uncertainty associated with the overall mean. And you get to this formula by using the uncertainty propagation law, applying to this overall mean calculation. If for some reason mean recovery varies very much significantly between the different reference materials, you can add an additional term there for that effect. That is the variance of the mean recovery, and we have to multiply by the square of n due to this denominator. And this is based on this VAMP project protocol equation. And but for trueness assessment, you need to do more than just calculate the overall mean and the standard uncertainty associated with the overall mean. You have to check if the overall mean is meteorologically equivalent to 100%, to the ideal value of 100%. And you do that using this t-test. And this is a meteorological assessment because this is a t-test where instead of a standard deviation, we have a standard uncertainty. So you have metrology there, not only statistics. And so we have the absolute value of 1 minus the overall mean divided by the standard uncertainty of the overall mean. If this is smaller or equal than 2, you don't need to correct the results for recovery. And you assume that the overall mean is 1 for following calculations. If this condition is not valid, you have to correct your results for the overall mean recovery by dividing by that overall mean, and you have to take that overall mean into account in the following calculations. So, and how should we combine the different uncertainty components? So, assuming that there is no other relevant uncertainty components, so the optimal approach is to divide our analytical interval in interval 1 and in interval 2. Okay, in interval 1, the expanded uncertainty of your measurement result is a coverage factor times square root of the square of the iterate precision standard deviation at interval 1. And then you have the sample concentration corrected or not corrected for recovery, depending on that t-test, times the standard uncertainty for trueness. And here you have the overall mean can be 1 or the overall mean itself, depending on the t-test too. For interval 2, uncertainty components are combined as relative. So we have the relative iterate precision standard deviation, the square of that. You have here the square of the relative standard uncertainty for trueness, and then you have to multiply by the sample concentration and expansion factor to get your uncertainty. So let's apply this to a specific case, termination of chromium in sediments as described in a paper by Carla Palma. So the analytical method was divided into intervals. Interval 1 between 1.5 and 10, this is 2 times LOQ, and 10 and 327 milligrams per kilogram. And here are the uncertainty components being combined, coverage factor of 2 for 95%, iterate precision standard deviation, the square of that, sample concentration, in this case correct for recovery, mean recovery, and here you have the trueness standard uncertainty, and equivalent for interval 2. If you study the performance of this analysis at 10 and 100 milligrams per kilogram, we get 1.3 and 13 milligrams per kilogram of our expanded uncertainty. Okay. Some years ago, Nortest proposed an alternative way of dealing with these systematic effects. The idea is to also to simplify the process by avoiding the t-test and decision to correct or not correct for recovery. The authors believe that this can be a problem, but this approach, although is a little more simple than the previous one, can overestimate the measurement uncertainty. So the algorithms proposed by Nortest to evaluate standard uncertainty for trueness, when you have several reference materials, the formula is this one, where I use the notation from the previously described approach. So what we have here, we have the overall mean there. Here we have the root mean square of relative errors. So this square of the mean recovery for each reference materials minus 1. This is the mean relative error, or the square of that. This is the number of reference materials, and here you have the mean of the square of the relative standard uncertainty for the different reference values. You apply and combine this approach. You combine the trueness component with the precision component as described previously, but in this case, the result here is always not corrected for recovery. But the other part of the formula is exactly the same. So if we apply this to that specific determination of chromium in sediments, we can have the expansion factor, the intermediate precision standard deviation square. So here is the trueness relative standard uncertainty from this north-test approach. If we apply this to the quantification of contaminated sediment with 10 and 100 milligrams per kilogram, we get 1.6 and 16 instead of 1.3 and 13. So the uncertainty increased 33% from this approach, because we have a bias that is significant of 8%. So the other thing that I would like to discuss with you is the fact that in some analytical fields you have regulated method validation designs that you have to follow, and these designs are frequently not set having in mind their use to evaluate uncertainty. Sometimes the collected validation data are correlated. There is some synchronism between that data that can affect the reliability of the quantification of measurement uncertainty. So we have to take that into account. Let me give an example. Termination of palladium in pharmaceutical products by ICP-MS, because palladium is used as catalysts for the production and some of active substances. So we can have that in the medicine. If we validate this termination by ICP-MS using ICH and USP guidelines, they suggest that for the validation you perform in one day the replicated analysis of a sample with typically native analyte before and after spiking. And you do in repeatability conditions, so same day, and then you have the spiked samples, and in the second day you analyze the spiked samples, and you don't analyze in that day the native mass fraction anymore. It can be challenging to use this data to estimate the determinate precision standard deviation, and you also must have into account that when the recovery is based on the results from day one, there is no between day precision effect affecting these recovery tests, where when you use data from day 2, we have the between day effects affecting that termination, and this should be taken into account in our uncertainty evaluation. So we have done that. So this is a collaboration with David Mild and Thomas Pluech, sorry for my pronunciation, and other colleagues, and we were able to handle this correlation of data to perform this top-down uncertainty evaluation. And we also discussed the impact of the uncertainty in the conformity assessment of this medicine. One of the sentences that I like most from this paper is the fact that this research shows that measurement uncertainty evaluation adapts to the specificity of the experimental data instead of being the other way around. So in uncertainty evaluation, if you know what you measure in detail, you can overcome some limitations that you think that your experimental data have. Let me close this presentation by some highlights. So the top-down uncertainty evaluations are pragmatic, but can be rather challenging. Um, we know, since we know how precision varies with the concentration or measured quantity, we can use that information to develop models of how precision varies with the concentration. Typically, you divide our analytical range in intervals below and above 2 LOQ. The way you manage bias affects your measurement uncertainty and, of course, measurement traceability, but that's another discussion. And you can adapt um, your uncertainty evaluation to the available validation design. Let me thank again the opportunity to present this topic. Let me thank from Lisbon to Prague and from Prague to all of you. Thank you very much for your attention.